Okay. Okay, so I guess let's get back. So this is what we told on last Tuesday. Oh, and I guess before we start teaching, so a reminder, we'll have our midterm next week. So it will be next Friday. And I think next Tuesday we might just skip the class so you can do the review yourself. I'm probably going to publish a review file, but the next Tuesday I'll be away. So I won't be here to host a review. Maybe I'll ask the TA to do review, but I'm not sure. Anyway, so next Tuesday no formal class, and this Friday we'll teach something that might not be midterm so much, but we'll see. I think so. Midterm, the range should be until chapter 3. So we'll finish the discrete-time Fourier series today, and but there will be some properties that will be probably taught on this Friday. But I think they are really similar to the property of the discrete-time Fourier series is really similar to the properties of the continuous-time Fourier series. So I think the whole chapter 3 will be in the midterm. Okay. Yeah. So question. 大钞比较麻烦，我想可能就不会给，对我们，对，但是我会给一些公式表这样子，对，对，应该没有大钞，但是有公式表，就是像这个公式表会给这样，技术。公式表会事先公布？对，我会事先公布，应该就是这个 table 吧 ，table 3.1跟 table 3.2这样子。我看一下，然后但是我们这里没有 Fourier transform 的东西，对不对？但没关系，公式表我们会事先公布，就应该这几天就会公布公式表。
可以带计算机吗？
计算机，应该计算机有点奇怪，应该是不需要计算机。我觉得不要好，对，好，其他问题吗？ Okay. Okay. If there is no question, then let's have a quick review of this time. So this time we go over the properties of the continuous time Fourier series. And okay. So we don't have one new. Oh yeah. Here we have the two equations of our Fourier series. Okay. So once again, analysis synthesis equation. We say we have our periodic signal x of t, and we think it's a sum of harmonic series. The harmonic series that are all periodic with period big T, and so we have those coefficients ak, and we think this linear combination of harmonic series represent our periodic function x of t. And then if we want to know the ak, then we can use this analysis equation to calculate ak from x of t. So we multiply x of t with this e to the minus jk omega naught t, and then we integrate over one period and take average, then we think it's ak. So we can transform back and forth between x of t and ak. And obviously there are some convergence issues, but we think our functions are usually nice enough that we don't have too much convergence issue. Okay. And then we have this big table of properties our Fourier series. So first they are linear. So if your signal is linear in x, then it's also linear in the corresponding Fourier coefficient. And okay, so this is really small. Can I do, let's see, this thing? Okay. Yeah. And okay. Yeah. And then we know if we do a time shift, then time shifting the signal, then the Fourier series coefficient will get HR, this exponential factor, e to exponential jk minus jk omega naught t naught. And then there is interesting conjugation property. So if we conjugate our signal, then our ak get conjugated, but also get basically flipped on k. So the corresponding ak bk will be a star minus k. And also if we do time reversal on signal, so our signal is x or minus t, then the corresponding bk will be a or minus k. And the time scaling is interesting, so time scaling doesn't change our ak at all. You become a of alpha t, then you still have ak, but this will change your big T. So yeah, so your period will become t divided by alpha. And then we have those convolution and multiplication property. We start with the convolution on our signal, then our series coefficient will get multiplied, and with extra big T here. And if we do multiplication on our signal, then we basically have a convolution on our series coefficient. And so this is this is the actual convolution here. Okay. So here this is a bit weird. This is a periodic convolution because x and y are periodic signals. So we're multiplying this x of tau and the y of t minus tau, but we're only integrating over one period. Okay. And then we have this weird differentiation property says that if you take dx dt, I guess differentiation property is okay. And we have dx dt as our signal, and the corresponding bk will be jk omega naught ik. And then you try to reverse this with integration property, and it's a little bit weird, so let's ignore that. And and we jump a little bit. And from this time reversal property, the conjugation property, we can derive something. And so for example, we can say if x of t is real, then we see that ak equal to ak ak equal to a star minus k, and you can move this around. This means a or minus k equal to ak star, and then you can combine that with real and even and odd property. Then you see that if you are real and even, your signal is real and even, then ak is also real and even, and so from the time reversal, you see that the even and odd property of ak is same as the even and odd property of your x of t. So and combine with real, then you see that the x of t is real even, ak is also real and even, and the x of t is real and odd, then ak is imaginary and odd, etc. Okay. And there is also this Parseval relation, says that if you integrate, so basically the energy of one period, average energy of one period of your signal equal to the total energy of your series coefficients. And we see that how these properties are useful is you can use them to calculate some of the series coefficient. So for example, you want to calculate the series coefficient of this signal, then we know that we already calculated the series coefficient of this signal, this black wave, and we think this up-down wave, this is really another black wave. So you can just do some time shift, time transform to make this signal linear transform this signal to this signal, and so you have the corresponding linear transform of your coefficient. So you can calculate the coefficient of this black signal. And then in the next example, we want to know the series coefficient of this signal. So this is kind of a triangle wave. Okay? And so we have seen so from previous example, we calculated the series coefficient from this black wave. And we see that the triangle wave is related to the black wave by differentiation. So if you differentiate this signal, you will become this signal. Okay? So that's easy to check, just check the differentiation. Okay, so differentiation of this signal becomes this signal. That means the coefficient of so you can relate the coefficient of this signal with the coefficient of this signal by the property we have here. Okay, so the coefficient of the differentiated signal is jk omega naught, times the original coefficient. Okay, so the coefficient is ek. So by the differentiation property, ek should equal to dk is the differentiation of this x bar. Okay, so so dk should equal to jk omega naught times the coefficient ek. Okay, so dk equal to jk omega naught ek, then ek equal to dk divided by jk omega naught. Okay, so we get our result. We already know dk from before, then we divide it by jk omega naught, we get ek. But that only works for k not equal to 0. For k equal to 0, then for k, so that only works for k not equal to 0 here. For k equal to 0, then you are divided by 0. Okay. And you are divided by 0, so you just calculate. So for E0, you don't really know. And that's represented by, because E0 is the DC component of the signal. So basically the constant component of the signal. So schematic is here, so you can think about your x bar of t is here. But you can think about if you have another x prime of t, maybe it's just a constant shift of x bar of t, and you see that those two signals will have the same differentiation, because the differentiation doesn't care about constant. Okay. So g of t is the differentiation of x bar or x prime. Then you only know the components of the signals. That's not a constant. Not a constant component. Okay. So for the constant or DC component of this signal, you just need to calculate it itself. And the constant component will be the average of those signals. So you just take the average of this signal over one period, and you see the signal is oscillating up and down between 1 and 0. And it's very easy to see that the average is 1 over 2. Okay. So you can calculate the average, and you see that it's 1 over 2. And then, for example, if you are calculating the coefficient of this x prime, that's actually between 2 and 1, then the DC component will be, I guess, anyone want to answer? What's the DC component of this x prime signal? Okay, it's the average of this signal, and it's between 2 and 1. So the DC component of those x prime signal will be 3 over 2. Okay, so yeah. For the DC component, if you are doing this reverse of differentiation for the DC component, you just take the average. Okay. Any question from this quick review? Everyone understand? Okay. Yeah. Okay. And so that's a review of what we had before spring break. And then now let's go to the actual topic of today. That's Fourier series representation of a discrete-time periodic signal. Okay, so that's a discrete-time Fourier series, and this is also called a discrete Fourier transform. Okay, that's just a name. Okay, and this is really similar to the continuous time Fourier series. And anyway, the idea is similar. So the idea is we have those eigenfunctions z of n. I guess it's a bit confusing. Okay, so we have z of n as the eigenfunctions of our discrete-time LTI system. So now we want to express our signal as a linear combination of z of n. But for some reasons, we actually don't express it as z of n. So we go back to the complex exponential. Okay, so we express z of n as e to the jk omega naught n. Okay. So just think z as some jk omega naught. Okay, and I guess this this expression makes the Fourier transform look more like our looks more similar between discrete time and continuous time. Okay, and so just like the continuous time Fourier series, now we want to express a periodic function as those complex exponentials. So we have a periodic function with period big N, so xn equal to x over n plus big N. And then we know that okay, so these things are periodic with period big N, and now we want to have those complex exponentials that's also periodic with period big N, and we know they are the harmonic related complex exponential. Okay, yeah. So the harmonic related complex exponentials also have period big N, and so we try to write it as this summation. So up to now is really similar to I guess we are jumping ahead a little bit. So let's try to close all the spoiler here. Okay. So we want to see our x of n as some summation ak. So we have a spoiler here. Let's close this out. Okay. X of n as a summation k, some ak, and those complex exponential that have period big N, and it's quite obviously here. Okay. This with this omega naught equal to 2 pi divided by n. Then this is e to the jk omega naught n. will have period big N. This is what we know from chapter 1. Okay. Okay, so our x of n are those things. And now we need to remember something more from chapter 1. So from chapter 1, we know that the discrete-time harmonic series is weird because this all go back to the discrete-time signal have this finite sample points. We have our discrete signal sample on integer points, and that means that even if this complex exponential has a really high frequency, you don't really see that. So here we have not very beautiful schematic. So we are thinking our discrete sample points are those 1 and 2 points. And so even if this complex exponential has a really high k, is oscillating really fast, it's still only sample point that is 1 and 2. So like even if okay, so I should draw better here. I don't like this. Okay. So let's try to draw better. So the idea is that even if so we are sample this point at the integer points 1 and 2. So if your signal is like 3 times faster than this 1 and 2, so let me try to draw this. So your signal is okay. It's me. Maybe let's draw an easier one. Okay. Your signal is oscillating twice as fast as those sample points. So I've seen this with better picture. Let's try to hand draw this. Oh. Erase. Why is this hard? Okay. So if you are twice as fast, like this, and because we only sample at the integer points, and the sample result is still the same as just the constant. Okay. Okay. And anyway, so what I'm trying to say is if your signal is oscillating really fast, and those discrete sample points don't really see the really fast oscillation, you only see what happened at the integer point. And the end result of this is that if this frequency k here increased by a big N, and yeah, so if this k here increased by big N, then this is really the same signal, okay? Because you get extra n here, and that actually only give you equal jn 2 pi divided by n times small n factor, and that's equal j 2 pi n, and that's just 1. Okay. And so that means that, so our spoiler here, that means that if you increase your k by a big N, then nothing really happens. And really, for the harmonic series of a discrete signal, you only care about big N consecutive terms. Okay. And so when you sum over those k, so sum over those k here, you don't need to sum k from minus infinity to plus infinity. So for continuous time, you sum k from minus infinity to plus infinity. And but for discrete time, you only need to sum k for this n bracket range. That means you sum over big N consecutive numbers. And there are infinite number of choices, but some of the ones you like is maybe your k from 0 to n minus 1, or your k from 1 to n, or even you can have k from 3 to n plus 2. Okay. And okay, so k can also be like 1 to n, so that's also something you like. And maybe, yeah. Okay. So that's our discrete Fourier series, and the first difference thing is our k is only range from some big N. Okay. And okay, and then from those equations, we want to solve for ak. And so one thing we notice is that those ak are pretty interesting. They are solvable by just by solving a linear system equation. So you can think about so your x of n is a periodic signal, right? So it has big and different values. So x of 0, x of 1, of x over 2, x over 1 minus 1. And if you just write it out, then x of 0 will equal to, well, just by this formula. Alright, x of 0 is the summation ak and e to the j0 omega naught n, so that's just 1, so it's a summation ak. And the x of 1 will be summation ak and e to the 2 pi j1 and 2 pi, j e to the j 2 pi k divided by n, and etc. And etc. to x of n minus 1. And then you can think about, you try to solve those ak, then you see that this is a linear combination of ak, right? So this is a0, a1 to a of n minus 1. And this is x of 1 equal to a0 and e to the j omega naught a1 and e to the 2j omega naught a2, etc. And you see that basically you have a linear system of linear equation for ak. So you have a0 to a minus 1, and with different coefficients here, and they equal to, so this is x0 to xn minus 1, you can think of it just as numbers. So basically here you have big N unknowns with big N equations, and actually you can show that those equations are linear independent, and you can solve those ak by just solving this linear system equations. Okay, and I guess that's a little different from the continuous sum case, where you have infinite number of ak, and you cannot really solve infinite number of equations. But here you have a finite number of ak, and so you can always solve ak by solving those linear system equations, and they are exact. And here is something we don't prove too rigorously, but basically from here we'll get that since you only have finite number of ak, the Fourier series will always converge for discrete-time signal. Okay, but that's that. This is a little bit of digression, and let's get back to actual work. Okay, so we can solve linear system equation, but it's a little bit annoying. And so we will mimic our continuous case and give a closed form solution to our Fourier series coefficient. Okay. And how do we do that is we use this orthogonal property just like the continuous case. So we have those property that you can prove in problem 3.5, or actually we also have a proof in later slide. But here, for now, we just have see this as an intuition. Okay, so we have e to the j and some difference in frequency. So some k minus r 2 pi divided by big N. So this is basically omega naught n. So e to the j and k minus r omega naught n. And this thing, just like in continuous case, this is n if your k minus y is k minus r is basically 0, and it's 0 otherwise. Okay, and why is this true? So first, so you can think about those numbers. So you are summing over bigger and different points on the complex plane. Those are complex number, and those are complex number on unit circle, right? Is exponential to the j something. Okay, so those are something on unit circle, and it's something on unit circle with the angle k minus r 2 pi, k minus r omega naught n. Okay. And so basically you are summing over these points on your circle, and with where am I? Okay, with this angle being okay. So you are summing over these points, and with the angle here being this is okay. This is 2 pi times k minus r over big N. Okay, so it's some fraction of 2 pi. It's an integer fraction of 2 pi because the big N is an integer and the k minus r is an integer. Okay, so the angle is 2 pi. It's some fraction of 2 pi. 2 pi times k minus r over N. And okay. And so if k minus r equal to 0, then this angle is 0. Okay, So k minus r equal to 0, then this angle is 0, and so you are summing over this 1 point. Okay. So you are just summing over this 1 point big N times, and you get big N. Okay. So this is very easy. So k minus r equal to 0, or even it can be multiple of big N. So multiple of big N means that this angle is a multiple of 2 pi, and you are still summing this point several times, and so you get big N. But if you sum over this exponential with this k minus r divided by n not being an integer, then you are summing over some equal division of this circle. And intuitively, you can think, so here we have this k minus r1 equal to 1 over 8. So you think you sum over is 1, 2, 3, 4, 5, 6, 7, 8 points. And they are equally spaced over the circle. So you think if you sum over them together, they will give you the original point equal to 0. Everyone understand? Okay. Anyway, this is intuition about this orthogonality, and but we're jumping ahead a little bit. This is the equation we'll use, and go back to our Fourier series. So we have this Fourier series representation: x of n equal to summation k, ak equal to jk omega n, and we want to find ak. And so just like in continuous case, we multiply this by another complex exponential with different frequency. So the frequency here we call r. So we multiply e to the minus jr and omega n. Okay, and we multiply this by both sides. And in continuous case we do integration, and in discrete case we do summation. So summation over small n. Okay, so small n over 1 period. So big N items. Okay. So here nothing really happened. We multiply this e to the j omega n on both sides, and then we sum over big N. And on this side, we just combine those two terms. So we have two exponentials. We can multiply each other. We can combine them by just doing the addition on their exponent. So we have k omega n and then r minus r omega n, and it becomes k minus r omega n. Okay. So nothing really happened. And and then what we do is on the right hand side we can change the order of summation. Okay, so it's sum n sum k, you can sum k sum n, and ak is not dependent on n, so we can put it outside. So sum k ak and sum n is exponential e to the j k minus n 2 pi divided by n. Okay, and so here we see why we want to discuss this thing. Okay. So this summation here is this summation here. So we can substitute this summation to this summation. Okay. And yeah, so this is just listing the equation we have once again. So on the left hand side we have our x of n here, and multiplying this e to the minus j omega n. And on the right hand side we have this summation ak, and this where the summation exponential k minus r and 2 pi divided by big N small n. And we know this summation is equal to only have value when k minus r equal to basically 0. Okay, and or k minus r equal to some multiple of big N. Okay, and so now we pick r. Okay, so if we pick r as the same range of k, and same range of k, then k minus r can never be those plus minus big N, so k minus r can only be 0 otherwise. Okay, and if we choose r in this range, then we see that we choose r in this range, then we see that well, on the left hand side it's 0 this thing, on the right hand side, then we see that when you sum over this n, when you sum over this n, then you see that you only have value when k equal to r. And so when you sum over this k, you will pick out only the k equal to this r. And so your ak will become ar. Okay. So you will have ak become ar because of this basic delta function. And and you have a big N from the summation of n terms. Okay. So this is really similar to the continuous case. And yeah, so we see how we get AR. Then you can do change the variable of R back to K, and you will see that AK equal to 1 over big N, summation small n, xn, e to the minus jk omega n. Okay, so that's the analysis relationship for discrete-time signal. Everyone understand? Okay, and then next we have a slide that basically a bit of a review and a comparison between orthogonality between complex exponentials. Okay. And so in the continuous case, we think we have two complex exponential e to a jn omega t and e to a jk omega t. And we want to do, so we kind of think them as vectors, and we have inner product between them. That means you take a complex conjugation of this thing, then multiply with this thing, and integrating over one period big T. And this integration. And we see that is 0 when k equal to is big T, when k equal to n, and 0 when k not equal to n. And you can write this as a delta function, delta of k minus n, and this is a bit weird because this is a continuous functions, but this delta function is a discrete delta function because this k and n are discrete, and times big T. Okay. And then we have I guess algebraic calculation here to show that y is 0 when k not equal to n. And also, I think we can skip that for today. This was done before. And also for discrete case, we have a similar thing. So now we have a discrete signal or also complex exponentials. Okay. So this complex exponential e to a j r omega n. So we use r instead of n because we already have n here. So e to a j r omega n and e to a jk omega n. And we do their inner product, and this inner product in discrete time is defined as we do a complex conjugation on this first function and multiply with it. So we have e to a jk minus r omega n, and then we sum over one period. So sum of the n over one period. Okay, and just as we said, this is those things is big N when your k minus r is a multiple of your big N, and it's 0 when your k minus r is other things. Okay, and once again you can think of I guess this is not quite a delta function, but okay, I think this is a approximate sign. Where am I? Yeah, sorry. This is I guess an approximate delta function because because k minus r can only so this is actually an impulse. So I guess that's close to this out. Not quite. This is an impulse train on k minus r. Okay. But but it's similar to a delta function. Your r is not ranged too much away from k. Okay. Okay. So that's that. And here we also have algebraic proof here. I think we can skip it. It's on the slide, and you can check it yourself. It should be pretty intuitive. You just brute force do the summation, and basically you can shift the summation a little bit and get the HR factor. And you see the HR factor is not 0, so your summation is 0. Okay, and okay, and we also have a schematics. This is a bit easier about why the signal is orthogonal. So here the integration part, we see that the integration when k minus n is not 0. Then you are kind of integrating over oscillating function, a sinusoidal or a complex exponential function. Then integrating over this function over one period, then it's just 0. But if k minus n equal to 0, then you are integrating over a constant function, and you get big T. And similarly for discrete time case, we just said before that if we are summing over this point with k minus r not equal to 0, then we are summing over equal partition on this unit circle, and it will become 0. And by k minus r equal to 0, then you are summing over this one point on your complex plane, and your summation will become bigger. Okay. So those are the orthogonality of complex exponentials. Okay. Any question about following? Okay. If there is no question, then let's have our small summary of our results. So for the discrete Fourier series, we have our synthesis equation and analysis equation. So synthesis equation, we have our periodic signal x of n equal to the summation k, ak e to the jk omega n. And our analysis relationship says that our ak is really similar to the synthesis now. It's 1 over big N and summing over the small n and x of n times e to the minus jk omega n. Okay. And here once again we have this weird simple bracket n. It's kind of like the integrating t we had in the continuous case. So this means over excuse me. This means summation over 1 period big N. And yeah, summation over 1 period big N, and means is whatever big N consecutive numbers. And you can start anywhere. So for example, you start from 0, then you sum from 0 to big N minus 1. Okay. So we have those two equations. And those AKs similarly is called spatial coefficient or Fourier series coefficients. Okay. And okay. And we kind of go over. So there is also something interesting happen with this k. Okay, so from before, remember we said that for the harmonic signals of the discrete case, this k only take a range from some 0 to big N minus 1, and because your k is from arbitrary 0 to big N minus 1, and also let's go back a little bit. Okay, remember this thing, and we also say this complex exponential when k goes to k plus big N is the same, and so really it's really natural to think our ak as just we can think our ak have a k in arbitrary value. So instead of just consecutive maybe 0 to n minus 1, you can think of ak in arbitrary k, and it's a periodic signal with ak equal to ak plus big N. Okay. Because this will work out in those equations. If you have k equal to k plus big N here, and you have this k plus big N, and this will be the same signal, you will get the same ak back. Okay. So really ak equal to ak plus big N, and ak is also a periodic signal with the same period big N. And so this is really interesting result as a discrete Fourier transform. Okay. And yeah, this reflects the specialness of a discrete signal. Okay, and then notation thing, just as we said, for the discrete Fourier series, we also call it a discrete Fourier transform. And it's called discrete Fourier transform because you see this is really symmetric. So you have a discrete signal and you get discrete signal AK, and they have the same period. Okay, so it's really nice. And also there's something we kind of go over, and we'll see this in more example, but there is no convergence issue for discrete Fourier transform. Okay, and I guess let's go to some example of how to find those Fourier series coefficient. And the first example is a really easy one, just in discrete case. This is an example where you can just eyeball the answer. So if your signal is sine omega n for some, okay. So now omega n, you need to be careful to be for this to be periodic function, as we know. So omega n need to be a rational multiple of 2 pi. But here our omega is just 2 pi divided by some big N. Okay. So we have a period big N. And then the sine function we can just write as a summation of two complex exponential. So 1/2j e to a j omega n minus 1/2j e to a minus j omega n. And from here, really you can compare to your x of n. Then you see that you have a1 equal to 2j and a of minus 1 equal to minus of 2j. Okay, and ak equal to other things. So your k should equal to 0 for all other ak. Okay, so here. And now here you see that you can pick whatever k you like. So maybe you pick your k because you have a minus 1 and a1 here. So maybe you pick your k from minus 1 to minus 2. Okay. So you have a minus 1 here and a0 equal to 0 and a1 equal to 1/2j. And all other ak up to k equal to n minus 2 equal to 0. And then we can plot our ak on a line. Okay, so ak is purely imaginary, so we put kind of plot the imaginary part of our ak here. So this is a plot of k. So plot of k and ak, and to plot this we need to pick a big n. So if we say big n equal to 5, then we see our ak is a periodic signal with period 5. So we see our a1 equal to this 1/2j and a minus 1 equal to minus 1/2j. And then the signal are really repeating itself with the period 5. So a4 equal to a minus 1 and so a4 equal to a minus 1 and a6 equal to a1, etc. And then we see that when we want to sum over back our x of n, then we can pick whatever range of k, right? So we just need 5 consecutive k here. So for example, the original one, maybe you were picking, let's say a really symmetric one. So maybe we have our k from this minus 2 to 2, right? Then we will pick up this a minus 1 and a plus 1. Okay. And but maybe we can pick some really weird range of k, right? And maybe we pick out, oh, sorry. No. Yeah, so maybe we pick our k range from maybe 5 to 9. Wait. Wait. 5 to 1, 2, 3, 4, 5. Wait. 1, 2. Oh yeah, yeah. So maybe we pick from 5 to 9, right? Then we'll have this a6 and a9, right? And so this summation will give back the same x of n because we know this a6 equal to a1 and also this k equal to 6 e to a j6 omega n equal to e to a j omega n because of the complex exponential discrepancy. And also this a9 will equal to a minus 1 and is e to a j9 omega n will equal to e to the minus omega j minus 1 omega n. Okay, so you can pick whatever range over this periodic ak. Okay, so that's the periodicity of ak, and we can have a more complicated example. So for example, but we still have sine and cosine, and this is still really similar to continuous case. So we have x equal to 1 plus sine omega n plus 3 cosine omega n. Oh, sorry, we have a different omega. So we have sine 2 pi over n and cosine 2 pi over n, and then we have this cosine 4 pi over big N plus pi over 2. And this is a period big N, and we have a higher frequency component here. And anyway, so period is still big N, and we can break our sine and cosine equal to complex exponential. And we've seen this multiple times, so let's give the detail. So I guess this cosine here, you have e to a j plus something and e to a j minus something. And this extra pi over 2 will become phase here. So it will become just e to a j pi over 2 and e to a minus j pi over 2. And you group terms together, so you have this e to a j 2 pi over n term with coefficient this 3 over 2 from here and 1 over 2j from here. And similarly, you have coefficient of every term, and you can really just read the coefficients from here. So the coefficient for 0 is just this 1, a0 is 1, and the a1 is 3/2 from here, and 1/2j from here, and so you have a1 and a-1 here, and a2 here, a2 from this cosine 4 pi n over big N, and a-2 here. You have those coefficients, and then all other coefficients are 0. And yeah. And once again, we can plot our AK as a function of K, and we see it's periodic. And here, AK is more complicated because they have both real and imaginary part. So here we are plotting AK with the absolute value and the angle. And anyway, we pick some big N here. The big N here is like 10 or something. Anyway, so it's pick some big N here, and again, yeah, and then we see our AK once again is periodic, and it's kind of symmetric between 0 because a0 equals 1, and a plus minus 1 has the same amplitude, and a plus minus 2 has the same amplitude, and yeah. But for the angle, it's not symmetric because a1 and a minus 1 have opposite angles, and a2 and a minus 2 has opposite angles. Yeah. Question on this example. So you see you have a periodic signal, and I guess here you can see that if you pick your K range smarter, then the signal will look nicer, right? So because your AK seems to have this nice symmetry, so you probably want to pick your K range from like here, and when you sum your AK back to your X of N, it's easier because you can combine the you can combine the positive and negative K equal to sine and cosines. Okay. Okay. And oh, we have enough time. Okay. So finally, the next example. Okay, so this is a bit interesting. Okay, this is a square wave example. So remember in continuous case, when we break our square wave to Fourier series and add it back, we got weird ripples at the edge because there was some discontinuity and there was a Gibbs effect. But okay. And so now we also have a square wave for the discrete time. So it's 1 from -n1 to n1 and 0 otherwise, and have some and has some period beacon. And really you can calculate. Okay, so let's skip the detailed calculation. So the detailed calculation is AK. You can put it into this equation, and it will be a summation of. Well, it's just a geometric series. It's a whole bunch of complex exponential. It's a geometric series, so you can put in geometric series formula, and then you have this sine over sine signal for your AK. Okay, and yeah, so you have your AK, and we can plot our AK. It's sine over sine, and it's sine over sine. So it's sine K, sine is K over sine K. And it's different from the continuous case. Continuous case is sin K over K. And so the continuous case it will decay out. But for the discrete case, it's just this oscillation. So you have a big oscillation sign and a small oscillation sign, like this. And for different N1 and N big N, and then you have a different AK. So we see that when big N get larger and larger, then your AK get a longer and longer period. And then really what we want to say is you have those series coefficient, but if you use this synthesis formula and add them back, they always add back to the same discrete square wave signal, and it's perfectly. And there is no convergence issue, and there is no Gibbs phenomena for the discrete signal, because basically you are transforming between big N variables and big N variables. And they are just linear transformations, and the transformation is exact. Okay. So you have a big N variable transformation back and forth. They are exact transformation. Okay, and so that's for today. And I think on Friday we'll wrap up So those we'll read chapter 3 really fast and maybe start on some of the chapter 4. Okay, so see you on Friday and good luck on your midterm next Friday. Okay. So 我等一下。